Hello. So make sure you can hear me. Yes. Oh, thank you. Thank you. Okay, very good. Very good. So let me try today to. So usually in a week number one, we only have one lecture, but this time we do have two. So therefore we can do something more about Mechatronics introduction. So we are going to continue the discussion. So what do you feel about the quiz number one? It's very simple, right? I hope you agree with me. It's really simple. Let me do the screen sharing by allowing the video, audio as well. Okay, so so we said that we are going to talk about what is mechatronics, what does that mean? So we're going to continue with that. So it is a synergistic combination of mechanical engineering, electronics, controls, control engineering, and computers, all integrated through the design process. Okay. Also, we discussed about mechatronics, about how this single word embedded this four parts. Okay, mechanics, electronics, control systems, and computer systems. Okay. So it is a refresher on complex numbers. You want to do that? Oh, okay. So yeah, it is quite important. You need to pick up those complex numbers. Yeah, let me do the comments so I can write on this. So I haven't uploaded our quiz number one. I'm going to upload after the class, okay? So you have until midnight, you can finish that. So, but I'm going to show you what is in the quiz number one so that you have no surprise. Let me show you here. So quiz number two. Week-01 quiz B is here. So basically, I hope you understand everything. So so you know that mecha is a mechanical tronics, electronics. CS stands for control systems, computer systems. Okay. Then I want you to list your mechatronic systems, and please don't say anything what we already said in the classroom. Like dryers, washing machine, your cars, and so on and so forth. I think you already know what's this, right? Okay, let's see. It doesn't matter. You can just use this line of paper. You can just write on top of this one. So I think it's a good idea. I do a different way this time. I do a different way this time. I'm going to do this way. I pass you this. I pass you this Week-01, and this is our. Actually, it's this one. It's 002. It's okay. We can use this one. So, what? My network is not connected. Give me a second. I just really. Can you hear me? Can anybody open the mic and talk to me?
Yeah, we can hear you.
We can hear you.
Oh, right. So because I switched my desk from different location, so I was checking. Everything should be fine, but why I cannot give you this file? This network, you can see there's a network disconnected. Resend it, still not. I cannot do it. So this is weird. You can see my screen, right? So TTM, I think I mentioned it last time, is time to market, right? Do you still remember what is a MAT? Modeling, analysis, and design. Okay. So basically, I tell you everything, but I want you to do something here. So I'm going to throw out some of the other CS. So first of all, we did the first CS is, okay, wait a minute. The first CS is control system. Second CS is computer system. What is third CS? Okay. This is the part I feel very funny. So imagine that this is customer satisfaction. Is there another CS? You do mechatronics and you have mechatronics design, therefore, what cool stuff. Who said that? Let me see. This is Daniel. You did a great job. Cool CS. So we already got the number 4. Any other things? Customer. Yeah. So let me submit one. So to you, you know, why Steve Jobs is great? Because he grasped our cognitive gap, that we always believe that we need a keyboard to type. That's wrong. He said, yeah, you don't need a keyboard to type. So remember the story of BlackBerry? Do you guys remember BlackBerry? Those with a tiny keyboard, you can type stuff. At a certain point, only like the president, BlackBerry smartphones, like president, like very high rank officers, they have the BlackBerry, you know. But eventually, everybody now gave up that. So without, great, thank you, Jesus. Without keyboard, it's okay. So this CS is actually cognitive science. So cognitive science. So they educate you about the cognition. So cogsci, okay. Do you know that cogsci.ucmerced.edu? Let me see if I can grab it for you. Cogsci.ucmerced.edu. Yep, we do have a very strong program on campus. These professors are world class, okay, doing cognitive and information science research. So therefore, mechatronics, from my point of view, is not just doing a good job in hardware, software, computer. You also need to think about functionality. You have more functionalities with lower cost. To have a custom satisfaction CS, you also need to consider another CS. So that CS is called cogsci. So in fact, what's popular in those big companies is called a UX department. Do you know what is UX? User experience. They need to study what is the best possible interface. So to study that kind of thing, then you need to understand the cognitive process in human users with the machine interface. So we do have a dedicated faculty member in the CS, ECS. He's doing a computer user interface, okay? So what is the science behind that is cogsci. So in the future, I hope when you see mechatronics, you should have a much broader view of mechatronics. So in the end, anything you create, Yeah, custom satisfaction. Thank you, Ravind. Ravind. Okay. Yeah. So in the end, you are going to create a Mechatronic system to serve people, right? So therefore, in the beginning of the design, you should put the user in the heart. Okay. So therefore, understanding that CS is another dimension you should pay attention. I mean, cognitive science. So I hope you agree. I think we already touched a little bit, almost there. CS. So C, if we see as a complex, S is system, right? So this could be a complex system, right? So because all the simple systems already done, what's left for you to do is already complex. So all those low-hanging fruits are gone already. So in the future, you have to do something complex. So then you have to go through the Mechatronics principle. Make sense? Right. So this list can go on. There are a lot of CS. There are many other CS. Think about it. There are many other CS. So be creative. Give me some good surprise about your interpretation of CS. Chicken sandwich. Nice. Nice. Cool. I don't, yeah, I'm okay with that. So if you create something that can be as popular as chicken sandwich, that's great. It can be cheap, can be useful like that. That's great. Yeah. Customer satisfaction, or they say that. So what else? Any other CS? Ah, there are many. I tell you, I don't want to give you my answers. I want to hear your answers. Okay. Communication system. Yeah, that's also good. Yeah, that's also good. Nothing wrong with that. Cool. Cool stuff is even better. I like it. So cool stuff. So in the future, and when you introduce to people, hey, I learned Mechatronics today, and so it has 4 areas, complex stuff. Yeah, yeah, cool. Yeah. I think another thing is I like it. So let's do this. I think I should say this. So I said it's a CS could be complex system, right? So I have a complexity that is simplified. Do you like it? So if you don't follow the Mechatronics principle, then you're kind of very messy, right? You create a very complex system and it's very messy. However, if you follow our Mechatronics way, it will be simplified. So like it. Give me a second. Okay, close my door. All right, so good. Now let's continue today. Here's the plan. So we're going to watch all those unwatched videos and explain to you the examples of Mechatronics. I hope you'll get inspired, and I hope you'll stay without dropping in the middle. And again, this is not an easy course. I warn you, and we have a few courses missing in a prerequisites. So it's the lowest possible prerequisites for us to learn Mechatronics. So having a Mechatronics course with lab intensive in your resume, people probably will look at you differently. We'll have a different plan for you. Yes, the quiz is 1B is supposed to be in a CAT course, but I cannot do it for some reason in my internet. It's always complaining, but I can use Zoom. It's very interesting. That's very interesting. Everyone, let me do one more time. Let me do one more time to see whether I can do it. For my computer from here. Here, maybe it's because of this. Try it again. Yay, this time is okay. That's strange. So check your chat box to see whether you can get that file. That's immediate, right? Can you? Can you check your chat box? Chat box? Yes, you can. So you can see I already showed you. It's simple questions. It's like this quiz is for memory. So in the end, you know what we chatted today, what we discussed today, right? So, and you upload it is evidence that you attended today's lecture. I cannot keep track of everyone as you see it. Okay, post on the screen so I may screenshot it. You can download a copy from that. So let me do this again. Yes, you can. That's another good idea. So then I need to make it smaller. How to make it smaller? It's here. Yeah. Okay, you can do a screenshot now. Okay, done. Okay, so it will be in the, usually it will be in the chat box. Sorry, it will be in the cat course, but today I moved my office and I somehow was not successful. So we are going to move forward. Yeah, it's in the chat box. It is already in the chat box. Luis, did you see that? Okay, good. You need to scroll back maybe. Okay, so let's do, we went through this explanation. Mechatronics is basically the design process. We put all the departments together. So then as a modern engineer, you have to have mechatronics training, that kind of notion, concept for the future, okay? So we talked about the system, and we talked about when you do closed loop, then the system, a stable system originally can go unstable if we not control it properly. So for stability, you also need to ask the question, how stable, okay? So how far away it is from unstable status, okay? So then we talked about the digital twin. I hope you visited our digital twin page, okay? So in this COVID time, we heavily rely on this digital twin notion. So next week, I'll join the lab discussion. So the first lab. So I'll convince you guys that you are not going to lose too much without putting your hands on the chip, on the hardware. So the digital twin will give you good training as well. So I talked about balanced foundation. Electronics is important. I talked about MAD, modeling, analysis, and design. I also mentioned a math book I wrote, published. We posted like 1,000 PPTs, PowerPoints of that textbook online. So you can download from that website. It's called Math Book, okay? Let me do an experiment together with you right now. So let me do this. I'll do a Math Book. So see what's going to happen. Math Book. Oh, Math Book is they thought I'm searching for MacBook. Oh, there is a mathbook.org. That's terrible. But let's say let's put a Merced here. Mathbook Merced. Gosh, this insists I'm going to search for the MacBook. That's wrong. No, it's something wrong. Let's put like UC Merced to see what's going to happen. Okay. Now it should happen. Really, still not showing up. Something wrong.
You should put quotes on the search.
No, let's say that put the one more. Yeah, maybe, but maybe they didn't. Maybe they didn't crawl that. It's okay. It's okay. Don't forget. So it's basically my lab mechatronics. All right. So you do a math book. You'll come out. This is our math book. So modeling, analysis, and design in MATLAB Simulink. So I suggest you guys should take a look at this book. Okay. There are a lot of PowerPoints, everything like 1,000+ PowerPoints. I even have English and Chinese version. And if any of you feel like you really want a copy of this book, sure, I can give you a copy, no problem. And most importantly, in this book, we have lots of figures, and each figures can be reproduced by downloading this zip file, and you unzip, you can reproduce the specific figure we put in the book. Okay, so it's pretty impressive. We put many years of effort on that. Okay, so, but only if you got bandwidth to want to enhance your study on control systems, the math part. So today, let's talk about dynamic system investigation. So we are facing a mechatronic system is usually a dynamic system. It changes over time. It has a motion. So if you have a falling rock, that's a dynamic system, right? Because at a different time, it's different position, right? So, the reason we study dynamic systems or dynamic system investigation, so we have a purpose to understand the system's behavior, being able to reproduce its behavior, that's a simulation, be able to predict its behavior, that's a model, and then we can predict what's going to happen next time moment, okay? So with that, I'm going to go through with you here. You have physical system, okay? Then you abstract to a model. Next week, we are going to start to talk about physics system, how go through a abstraction process, okay? Abstraction process. So you imagine that if I write x double dot plus, c x dot plus kx equals, I add a force in here, okay? So if I write, this is a differential equation. They didn't say, so it is here. We are talking about here, okay? But this one could be corresponding to what? Mass, spring, damper system, right? This is also could be in a later part. You probably already remember it is RLC, second order system. Can also lead to the second order differential equation, right? So then you can see the components are different in here, but in the end, the math model is the same, okay? So, in other words, the math model is another layer of abstraction from the physical model. And physics system to physical model use KCL, KVL, Ohm's law, constitutive relationship about capacitor and inductor, or use Newton's second law and so on and so forth, right? And damping and spring, Hooke's law, and all those are physical system, physical model. But if you write in the math equation, they are the same. So in fact, we are going to talk about the duality, dual system. So you can use RLC, resistor, capacitor, inductors to construct the system that will behave exactly the same as mass spin damper system. Okay, so that kind of they could parallel or duality, duality. Sometimes you heard about it. It's called emulation. Emulation. Okay, emulation. Okay, you're doing emulation. So this all we need to go through everything here. Okay, so do mathematical model. You do some analysis. So what kind of analysis? Okay, so I want to understand when the coefficients C and K will be configured such that the system is a non-decaying oscillator, like then it's always oscillating. So that answer that question is a mathematical analysis. You also can say, oh, what is the resonance condition? It's exactly the same question, and so on and so forth. So there are lots of analysis in here. But in general speaking, your analysis only happen in either time domain or frequency domain. Okay, so we are going to talk about this. Okay, we're going to learn the skills here. Okay, so then when you see the behavior and you also have behavior from the real physics system, then you can compare with the physics system behavior. So you do this comparison. Frequency domain. Frequency domain. Okay, sorry. Frequency domain. Time domain, frequency domain. So remember that you are living in the world. You look at the things, usually it's time domain, time history, right? Time domain. But you also can see it in frequency domain. We are going to look into that later. So I hope you can study something on the circuit theory. There's something called SSS. Do you guys know what is SSS? It's called sinusoid steady state, where you probably have heard about phasor. You have heard about magnitude, change of frequency. Okay, you heard about, say for example, you have an equalizer for those music DJ keyboard. There's some knobs up and down, that kind of thing is to change the frequency emphasis. Okay, so you hear differently, right? Like stronger, low frequency sound, or you have some metallic rock, and so so you can change that. That's basically a change in the frequency domain. Okay, frequency domain. So you have a low pass, high pass, band pass, band stop, and so on and so forth. Those are filters. Yes, you're right. So when we see filters, so filter what? So usually you mention that filter in the frequency domain contents. We're going to go to that part later. So this is just like a mile-high overview. So don't worry if you feel puzzled on something, just ask. Thank you, Gualberto. Okay, thank you. So keep asking. I love interactions. And we have one extra lectures. So it's a bonus for the week one. Usually week one we'll lose one lecture. But we are glad we are on Wednesday, Friday. So on the other hand, isn't this nice? After Friday, you are, so basically this course, I am standing between you and your weekend. So beautiful, right? Then you compare, you adjust the physical models. So the modeling part itself is a huge topic, can be dedicated course, a semester-long course about system modeling. Then of course, we need to have a foundation coverage about modeling. What is modeling? Why modeling? What kind of modeling we may have? Okay, so on and so forth. when to choose what model format, and so on and so forth. We're going to cover that part. You probably already heard this transfer function, state space. If you haven't, don't worry, we're going to cover it. Okay. So this is even more detailed explanation about what I already explained to you. Okay. So it's called how we can do dynamic system investigation. First of all, we respect the word dynamic. Okay. Dynamic. So because it changes over time. Okay. So we hope we will be able to predict its behavior. And we wish we do not just live with this behavior. We are hoping the system's behavior will behave in a way we asked it to behave. For example, your room temperature is a dynamic system, and it's a behavior of that room temperature system. It's a dynamic system, it changes, okay? But I hope it will not change. It will keep at 70 Fahrenheit. So you need some regulation, sense feedback and on and off your heater or central vacuum, this air conditioning system. So it will be closed loop control. So why we need to do control? The control is to make the system to behave as we wished. Okay. All right. How to decide the control? Well, you need to know what do you control, or what do you want, what do you have, okay. The knowledge. So then you need to have an understanding about the system. That part is called modeling. Okay. So the ID stands for identification. It's not like you put ID here. You have a student ID. So that's identification of your identity. But for us, identity is talking about a model. Model, not only you have a form, what form of model, but also all those coefficients, I call parameters, involved in there. Let me go back and show you. So this is itself is a form, but so these numbers, these are coefficients, okay? So parameters. So although you know the form is there, but you still cannot say this is your system. You have to decide what are the parameters. So all this process is called system ID, okay? System ID. So we are going to talk about components that we can use those building blocks. The building blocks, you played with Lego, right? So there are only some basic building blocks. Then you can build your physics systems. Okay. So those blocks like a resistor is a building block, capacitor is a building block, inductor is a building block. So then you combine them together. So it will be a dynamic system, right? The same is true for mass spring damper. Same is true for thermal system. Same is true for fluid systems and so on and so forth. Okay. All right. So we have seen the concurrent is just you do simultaneously. So it's the picture. Let's go through that. Concurrent is not concurrent engineering. In concurrent engineering, you just bridge the design and manufacturing. Okay, design and manufacturing. So those electrical, mechanical control computer systems operate in a separate environment. So this is called vertical integration. However, mechatronics, you need to have a vertical and horizontal integration. Okay, so that actually showed in this picture. Mechatronics. Okay. So it's also not just the electromechanics to make things electrification. So previously we treat them separately, like you have motors, solenoids, generators, then control them, start up, stop, AC motors. All these things is electromechanics. Okay. We are going to cover some of these in the actuator section in the later part of the course. But for Mechatronic system, it's a closed loop all in. I think recently in Silicon Valley, there is another term similar. Do you guys know what's that? So they want to hire somebody who can do what is, maybe I'm wrong. Is this called full deck or something? Or maybe full deck? Basically, the whole cycle, every detail, you know everything about it. So it's just like a company CTO. If some employee quit or sick, this CTO, he knows everybody's work. If needed, he can replace him. So that mechatronics system, mechatronics engineer should be trained in such a way they can do all parts, from actuators, sensors, control system design, computers in the design process, and synergistically combine it. So before you design the system, you already have the whole system in mind. There was a term in Chinese, say, for example, if you want to paint a bamboo, this bamboo, you know, this slender like bamboo, right? So you want this paint, oil paint or whatever, paint bamboo. In your heart, you should have the whole bamboo in your mind. It's not like you just draw a leaf, then add a branch, and then you add, you know, the trunk. It's not like that. So you have the whole bamboo in your heart, in your brain. Then you can draw them. You see what I mean? Yeah. So the mechatronics something like the same. You have to have the whole system. Then you have different parts synergistically combined together. It's called full deck. Yeah, I think it's called full deck engineer. Full deck engineer. So on the other hand, I call myself a hardcore control guy. Okay, hardcore control guy. I may have a bias saying that, oh, control is so important. I don't want to say that now. I want to say mechatronics is way more than just controls. Control is only part of the whole thing. Make sense? So mechatronics draw heavily on the concept of control system. Okay, so of course, if my philosophy here is, if something is not under control, then it's what? It is out of control. So you don't want something out of control, right? So if you are out of control, you can even stand. You cannot even stand straight upright. Upright. You stand upright. It's under control. Okay. Yeah. the same thing is true for a society or government or country. With the power without control is corruption, right? So, okay. So control is important, of course it's important, but you have to have other parts, the whole mechatronic systems. So it is integral component to any of the mechatronic design. It's not like, oops, later on we add those controls there. So again, you need to have a big picture first. You need to have a synergistic view of the mechatronic system, okay? So I'll mention the controls. Yeah, I want to say I know almost all control related technical stuff, okay? It's very rare to find something I never heard about it. So anything control, ask me questions. I'll have answer for you. At least I know where to find the answer, okay? Okay, I promise. So if you say, Dr. I want to control myself, that, sorry, I probably better luck this time. So you have to control yourself, okay? If you are controlled by others, then you are not a free man. You are in prison, right? Good job. Thank you, Greg, for the humor. Liz, thank you for showing. Haha. I like this feedback. So I think we talked about the Mechatronics benefits, you name it. So there are something interesting to talk about here: quality, reliability, performance. I think there's another important term they forgot. Let me add it. What is P? Nice. Profit. Nice, Daniel. Okay. Profit margin. So although some industry people may say, go away, and I'm busy, and don't sell me your mechatronics idea. But you say, look, although I know you are making profit, but do you need a bigger profit margin? Or bigger, more consistent? Okay. It's not like sometimes you have a more profit, sometimes it's less. So it fluctuates. But what if you need some consistent, larger, more consistent and larger profit margin? Then Mechatronics will be able to help. Thank you. That's smart. My class is smart. Thank you. Low cost. Oh, now I recall another CS. Because this cost remind me. Cost sensitive. We got another CS. Oh, no. Cost saving. See, I already got two new. So please add something that belongs to you. At least the final one belongs to you, okay? But otherwise, you can recall what we talked. I think we already talked at least 6, right? CS. Okay, maybe 8. So maybe we can collect 10. So depending on our creativity, okay? Yeah. So write more to impress, okay? Okay. So the conclusion is there are a lot of benefits, but you should be able to expand the justification. Just not like kind of a lot. That's not enough. You need to say like more specifically, like shorter development cycles, short TTM, time to market, lower cost and cost saving, make customer happier, and increase the quality, reliability, performance, and benefits. I would like to say everything here has direct or indirect with another important term everybody is talking about. Do you know this term? Starting with S. What's that? Okay, sustainability. Yes, sustainability. Great, Jesus, good job. So in a nutshell, as an engineer, we want to create something to make our world a better place. Not only for us, but also for our kids in the generations to come. Okay, so the world is more sustainable. Okay, sustainable. So therefore, I do have a yes, sustainability. Yes, yes, John, sustainability. So mechatronics and sustainability, I believe, is tightly, directly connected. So in the future, I hope everybody will be able to justify, okay, say more about how mechatronics contribute to sustainability. Not just one sentence. I hope you can write a half page on that. So that's the reason I ask you to do in the homework. And I'll give you a reading. So people already are talking about this. So it's a more recent topic. So you should feel proud you are doing your part. Get ready to contribute to the sustainability. Okay. Do you know that our UCMRC is #1 in the world in terms of green campus and sustainability? Do you know that? #1. Okay, the #1, but it's not among the #1s. Oh, probably haven't heard. You should go to the news section for the UCMRC about net zero. Yeah, carbon neutral. Yes, yes. That's Daniel. You are great. Thank you. We are the first university in the world achieving that before the end of last year. Carbon neutral. Yes. Yes. Every university should have some #1s on some aspects. So, yeah. Our UCMRC has lots of #1s we feel proud of. Do you know that we have the largest reserve system next to the campus? I serve on the reserve faculty advisory committee. So that reserve is 7,000 acres. Okay, 7,000 acres, huge, and it's just next door. You don't need a long distance driving. So that keep an eye on that. And you can also request hiking in there, do some activities as a group. And we are planning for few million dollars expansion for so inside you have classrooms, you even have a lodge. The people from far away can stay, do some research on this reserve and sleeping in the cabin. They have restrooms and so on and so forth. And everything is off grid and it's fun. Yep. So sustainability. In the homework part, I already can show you that it's next week. Let me see, I did it already. Do you see my screen? Yes. So basically, I'm going to ask you to write mechatronics and sustainability, your perspectives. It's not half page, but not more than 3 pages. So, all right. So force yourself to read more and write something, expand discussion about this, okay? Those other problems are specific, checking your prerequisites, checking your preparedness. So wake you up. So these are just for you to wake up, okay? Warm up, let's say that way, better. Warm up, okay? All right, so we talk about mechatronics, benefits of using that. It's directly or indirectly contributed to the sustainability questions. So for mechatronics, I would like to say mechatronics is not just motion control, okay? Because traditionally people always say, oh, I have a motion control for some mechatronic system. So for example, a robot, a drone, or a tractor. So those are things are moving, okay, moving. But I would like to say, because it's a mechanic system, in a mechanical engineering, you are not just motion or dynamics, you know, you also have thermal fluids, right? The thermal fluids, okay? So I think that's also mechanic system. Can you say those are not mechanic system? Yeah, so here they're talking about high speed, high precision, high efficient, high robust, macro miniature, all those things, implying something with motion, okay? Motion, this one, you have motion. But in reality, you could have a mechatronic system that is no moving parts. Make sense? So you have thermal system. Say for example, your HVAC system. This is also a mechanic system, right? So mechanic system, you have thermal fluids and motors, okay? Okay. So therefore, we are also treating everything in a unified framework. However, our whole semester will be heavily, will be, oh, this is nice. Heavily in motion controls, okay? So basically the actuators will focus more on the motors. So with that, you will see driverless car, unmanned aircraft systems, unmanned tractors in the field, and you just name it. Those mechanic system involving motions. So that we focus more on this, okay? But we also mention thermal fluids, okay? So don't get me wrong, okay? So the message is you need to think systems. So as a whole. So I said, I hope you will see a forest instead of just to see a tree or individual trees. Or as I said, when you want to paint a bamboo, you should have the whole bamboo in your heart, okay? So instead of just see the components, leaves, branches, and so on and so forth. But from a mechatronic system, and if we emphasize on the motion control, we talk about direct drive mechanisms. Mechanics is simple. And we also need to consider the system complexity. So if you have many moving parts, the system will have problem of reliability eventually. And what you can get from controls, okay? Sometimes it is not accurate, but after control, everything is accurate. But control is not a panacea. It's not a cure-all. So there are fundamental things that you cannot control to that level of accuracy. So do you hear that this term? So say, if you cannot measure, you cannot manage. You cannot manage. If you cannot measure, you cannot manage, okay? The same is true. If you cannot sense, you cannot control, okay? The same, okay? It's the same. If you cannot sense well, you can control well. This is philosophically true, right? Yeah, it's true. So there's also a Chinese saying about this parallel. Say if you are an artist doing a sculpture, okay, so you make a sculpture, okay, using chisels and stuff like that. So the saying goes, you cannot make a great sculpture from a piece of rotting wood. Okay. From the it's double T, rotting wood. You cannot make a brilliant sculpture from a rotting wood. So that also verifies you have to have a good sensor, so you have good control. You cannot have like a bad sensor, you have good control. Don't dream about it. Okay. Okay, great. So this is something to make you feel good. So in the industry, you mechatronics engineer usually will be in a good position to serve as a leader. So then you have initiation, meaning you propose, you suggest, okay, you having that initiative and integration of design. Then you have a broader interdisciplinary knowledge, okay, ability to master entire design, the whole design process from concept to manufacturing. Use the knowledge resources of other people, okay? This is important, okay? Many years ago, actually that was 1985, okay? 1985. When this is my last year in the university, we'll do a capstone design. It's also called a senior design. At that time, if I look back, I feel like I'm among the very few that had an interest to know what others were doing, because I'm just willing to learn what others are doing. So I think I kept this type of curiosity, and I understand who knows to do what, okay, or who knows to be expert on what. It's as if I have access to those expertise. So this says that, okay. Of course, today we have Google, but Google has its own limitations, okay. So you know what I mean. So it's not just that you do a best job, you are all that good. It's not enough. You have to have a good knowledge with people and with their expertise, so they serve as your resources. And then how to blend them, okay, provide the most optimal design solution. So, yeah. So area of study, we already talked about it. So the week one, we're talking about all these principles. We're talking about MAD, MAD. So this electronics part is, we have a course missing, okay? But I'm going to make up this one for you. It's called op-amp. And digital controls, okay? Digital controls. And we are going to do actuator sensors. We'll talk about a little bit on this interfacing sensors actuation. Real-time programming, I think it's less important right now. You don't want to do a real-time control code from a very low level C code or even assembly. No, today everything is more at this level. It's called hardware in a loop. Hardware in a loop, real-time control. So, and others is an advanced topic like how you do a physiologic control, smart material. That you can add many, okay, many. You can add many. So, but we probably will not do magnetic bearing. We're doing a position or speed servo and stuff like that. So let me show you one movie. We talked about interesting. It's called inverted pendulum on the card. So basically, you have a card, and on the middle of the card there's a joint. So if you move fast, the pole will go. You move left, the pole will go to right. Okay, so you go to right, then they will go. So you adjust the vehicle, the wheel, then we maintain the pole upright. So this is called inverted. So we're actually using a high school physical type of physics experiments. This is there's a lot of small holes. You blow the wind inside, so you move this cart through this motor. This motor going up and going this way, then this motor will pull the string. So this side is string, this side is, so the motor will do this, and the string will pull left and right. So as if you have a moving cart. And this moving card is sitting on top of this scale. This scale is used for air cushioned so motion to tell you that the friction is different when you blow different wind into it. So, but the question is how you measure this, how you turn this motor here. This is the motor here. How you turn it such that you maintain this upright. Okay, so that's not easy. So you assume that you can measure there's encoder in here. There's also encoder in here, like how many distance you traveled. So let's see it. And also I want this card stay here or stay here or stay here. So it's called square wave. Okay. So you need some adjustment to make it upright. So this is a typical mechatronics control example. It's actually very difficult to control. You need to use a lot of modern control ideas to make it work. Okay. And this is giving a square wave. You can do this. So what if I just showing that the whole system is robust? So you can see the system is working. But what if I add some tip mass on it? On the tip, I screw something on top of that, whether it will still work? Okay. It is so reactive, so like it has the noise is because of the blowing of the wind. You see that? So does this one remind you something close to Boston Dynamics? That's cool. So in fact, it's is similar idea. So it's called a robust adaptive feedback control. So that is a reactive, you know, kind of thing with added tip mass. So when the system works, you add a tip mass still work. This actually is called robustness. Robustness. You should know this term from now on, robustness. So if you want to do something that is so, when they get pushed down, doesn't matter. They just can get up. They don't feel the pain though. So only you feel the pain. So yeah. So this new year they did group dancing. It's pretty cool. Again, yeah, they have to have very good control in there. So to me, they are also Mechatronic systems. They are controlling the motion. Okay, so I think you have seen this thing. So unfortunately, we cannot do the experiment like this. However, we can do something similar. We can do something similar, almost like a real, yeah, from a digital twin setting. I'll talk to the TS whether we can do this type of inverted pendulum. Okay, maybe you can design. In fact, we have a hope. You design a lab. It looks like this. Okay, almost like this. Yeah, you have a motor, you have pulley, you have a wire, and you have the cart on the scale. We can adjust the friction by adjusting the air pressure, air cushion. Yeah, it's a very nice system. I miss it. It was done when I was in Utah State University before I moved here in 2012. Do you know that I am 9 years old on campus? Yeah, I'm here pretty long already. Goes very fast. Well, we have a few more minutes, and what I plan to do next is to show you another deck of slides. But on the other hand, you don't really have to. We don't really have to go through them. So it's a very big file. So I want you to take a look because, as I said, this is nothing but a Mechatronic system. I want you to take a look. Okay, I wanted to go through, but I prefer you go and read it. Okay. So perhaps many of you will get into the industry and work on unmanned autonomous systems. Okay, so I hope you will be able to appreciate what's inside, how we can approach this unmanned autonomous system. What is the Mechatronics synergy in there? Okay, so with these questions, go and go through those slides. Okay, go through those slides. But on the other hand, I want you talking about unmanned. Okay, do you know that for any unmanned system, yes, I'll give you the submission link after the class. Okay, yeah, I'll do that. Do you know that there is no such thing called a 100% unmanned system? If that's true, the world is in danger, right? So it's funny. Let me show you one slide. This is the hog. I didn't plan to show you all these things. These are the talks I give. So one of the talks is about citrus. What? Oh, yeah, it's here. I just want to show it's a November 12th. That's our future, isn't it? So Skynet, yeah, it's from Skynet. Okay, so perhaps this is a typical scenario in the future in San Francisco, and yeah, this is okay, Roberto, you are right. So what I'm trying to make is behind every unmanned system, there is at least one man or woman. Okay, so we're talking about the future remote work. So probably in the future, you don't go to grocery store. The pandemic is severe. So then you have your avatar goes out, or you have an exoskeleton that help you to be able to walk longer time. Okay, and either way. Okay, so unmanned system is never really unmanned. Okay, so my point is there's at least one man behind the unmanned system. The point is they could be unmanned if needed, but if it could be manned if needed as well. So that's the point. And in here, you are going to see a lot of slides, but I want to highlight one slide to you. Yeah, this is okay. This is a slide, so that you can watch. You can watch what Dr. Chen looks like when he was young. So this is called undercar inspection. They can, it's a very low profile, so they can go underneath the car to check what's there. And it is actually widely used in, this is a picture. It's actually widely used in Baghdad, in the street of checkpoints, so on duty in Baghdad. So it's real, it's widely used. So this whole system is unmanned autonomous system, but there is a man in command when needed. Okay, so it is a Mechatronic system. So then you can see the Mechatronic system, you need to have subsystems. Okay, so the whole vehicle, you have mechanical, sensor, control, software, computer. Yeah, then you have electronics. So it's a Mechatronic system. But also they added something interface with human, like how to understand this human's behavior, intelligent behavior, and so on and so forth. So I want to stop here. I'll let you explore this deck of slides I already uploaded in the folder. So it's 106 slides. That's a lot. So I want to stop here so that we can stop on time. Let me see if I have any chat questions in here. Yes, great. Yeah. It's required to have at least one person in case it lost control. So we have a lot of other things like safety, security, and liability. So if something goes wrong, who is liable? Who is going to pick up the ticket or bill, okay, or penalty, and so on and so forth. Well, I think it's good time we've finished here, and I'll upload this lecture, and we are going to meet again next Wednesday. But we probably will meet next Wednesday morning. We have a lab. Let me check. Our calendar for the lab is next week. Yes, we have 1 o'clock. We have office hour. Okay, we have office hour. Well, why I don't have my lab in here? No, I didn't put in my lab. Strange. So we should have a lab. I think we should have a lab. Let me see. sorry, we use a little bit more time. So the lab is Hyro's lab. It's next Wednesday, 9 o'clock. Okay, great. I'll see you next Wednesday, 9 o'clock. Okay. So we are done today. Thank you. Have a productive weekend. Okay. Bye-bye. Thank you. Thank you. Bye. Take care. Don't go to a crowded space and keep distance. Wear a mask. Okay. Take care. Bye.